In this section of the book, I want to talk about mass and density. This is a more kind of serious application than maybe volumes and surface areas that you may find a little difficult to believe you would ever use to calculate anything with. We're going to have to use some concepts from multivariable calculus, calculus with many variables. We're not really going to use them. Hopefully you'll have some intuition for them, but I'm going to state things the way you would in a multivariable class initially because we need to talk about the density of solid objects, and that a solid object has 3 dimensions, and that's naturally a topic for multivariable calculus, but I think you'll be all right. I'm just going to say it very intuitively, write some notation that looks like integrals, and hopefully I think you'll be fine. You probably have an intuitive idea of what density is. Density, you know what it means. You know what it means for one object to be more dense than the other. It kind of means, it's heavier for its size. Yeah, density is mass per volume. So it's mass divided by volume. So that if you fix the mass and make the volume very big, the density would be low. Yeah, so something that's big that weighs a lot isn't as dense. I said weighs a lot. There is a difference between mass and weight, and I want to say something about that. But so density, mass per volume. But you may never have thought about instantaneous density, that objects or liquids or just various things can have densities that are different at different points in the object, like humans. The density at various points in your body is very different. So what is instantaneous density? Well, you might be able to guess if you have some solid object, regardless of how weird the shape is, what should the density at a point mean? Well, you take a very small volume around that point. So think of a rectangular solid. Take a little rectangular chunk of your solid around that point, very small. So take a rectangular solid chunk around that point and take the mass of that chunk and divide by the volume of that rectangular solid, which is its length times its width times its height. And you do this for smaller, take the limit. The density would be the limit as you take smaller and smaller volumes, smaller and smaller rectangular solids around that point, and take the mass, divide by the volume, and you get an instantaneous density. We like to use lowercase delta for density. Delta P, the density at P. And it's defined by a limiting process, as you might expect, but it's a multivariable limit because there are 3 dimensions. They're getting small. But hopefully that's intuitively clear. And what it means is you should think of it as the instantaneous rate of change of mass. So this is mass with respect to volume. So yeah, density is mass per volume. If the density is constant, you just take the total mass divided by the total volume. But in a calculus class, you take instantaneous density, the density at each point, defined in this limiting way. If you write this in differential notation or think infinitesimally, this says that the infinitesimal amount of mass at a point, P, is the density times the infinitesimal volume, so that if you were given a density function and you knew how to do integrals in 3 dimensions, what this would tell you is that the total mass, so what you would get is that the total mass would equal the integral of, the continuous sum of all the infinitesimal little blobs of mass. What should you write for limits of integration? Well, some notation that means you're integrating over the entire solid. So this notation, I'm just I'm just reading it, integrate, so take a continuous sum of the mass of dm, little infinitesimal plasma mass, as your points move throughout the entire solid. So this notation isn't helpful for calculating. It's just telling you what we're doing. And so you would do this kind of thing. dm is the density times dv, so I need to integrate, so take a continuous sum of all the infinitesimal contributions you get as your point P moves through all the points in your solid S, and you take the instantaneous density times little infinitesimal chunks of volume. Great, you can say all this, but this is a course in single variable calculus. And so the question is, where do we get a one variable integral from? How do we set things up so that we can do something like this just in terms of a single variable? And it just means that our solids have to be fairly special, but we can still do interesting problems. So here's our solid. What we're going to assume is that somewhere you've got an axis, and I'll call it the x-axis, and that your solid lies between the perpendicular cross-sections, perpendicular planes to x at x equals a and x equals b. So your solid lies between the cross-sections where x equals a and x equals b, and that for each x between a and b, we're going to assume two things. One of them is what we assumed when we looked at volumes. Namely, we're going to assume at each point x along here that we know ax, the area of the cross-section at x, of the, I'll just say x cross-section. And we want this area function, this cross-sectional area function, to be continuous so that we can integrate it. And what else do we have to assume? Well, we want to calculate mass. So we're going to have that little cross-sectional area will give us a dV because we'll take, as hopefully you recall from the section on volumes, we'll just take ax times an infinitesimal little change in x. That, remember, that thickens up this slice so that you get, that thickens up this cross-section so that you get an infinitesimal little chunk of volume. So that'll give us this dV, but we would need a density that depends just on x also. And what that means is we need to assume that while the density throughout the object can change as x changes, that if you fix an x, if you take a specific x value, that all the points in that x cross-section have the same density. So we also need to assume that we have a density function that depends solely on x. So, and once we do that, we'll be able to do these problems, or some interesting problems. So we also assume we have a continuous function, delta x, which equals the density at each point in our solid in the x cross-section. So I am assuming that the density of the solid does not change in a given x cross-section. So all these points would have the same density, but as your x changes, then the density of your solid can change. All right. Once we have that, then this mass integral will get a lot easier. We will integrate as x goes from a to b, we'll add up. So as we go from here to here, that will take us, by looking at cross-sections, that'll take us through every point in our solid. And so we'll take the integral as x goes from a to b of, now we'll have a delta x times dv, but we know dv is a of x times dx. It really does help to break the problem up into pieces. And when you're thinking about physical applications of integration, you really should think, oh, the total mass. I add up all the infinitesimal pieces of mass. How do I get a little chunk of mass? Oh, I take density times, something I've written that's wrong. Hopefully you notice this. You take, right, this should be a dx. You take the density times a little chunk of volume, but then you think, oh, but a little chunk of volume is the cross-sectional area times dx, or whatever your variable is. And so, yeah, you split up the problem into pieces. Okay, so this is what we are going to do. But first, I want to say something about the difference between weight and mass. So you're probably familiar with mass in the metric system. The standard unit of mass in the metric system is the kilogram. People often, when they're speaking about it, just call it a kilo. It's short for kilogram. That's the unit of mass. That is not weight. That distinction gets blurred in common speech because many people from Europe will say that, oh, I weigh some number of kilograms. So, what do I weigh? I weigh 70 kilos. They don't really mean that's what they weigh. They mean that's their mass. There's just no good verb form of the word mass. But what you weigh, weight, is the force of gravity that the force of gravity exerts on a mass. So it's the mass times the acceleration of gravity. So weight is a force, and 1 kilogram, to get its weight, you would actually multiply times the acceleration of gravity, so that's roughly 9.8 meters per second squared. So the 1 kilogram weighs roughly 9.8 newtons. Now, nobody talks about weighing a certain number of newtons. In theory they should, but they don't. The situation in the English system with pounds and feet is complicated in another direction because almost nobody talks about the unit of mass in the English system. It's so let me come over here and write that 1 kilogram, if you assumed you had newtons first, so the unit of force first, 1 kilogram is 1 newton per meter per second squared. All right, that's a kilogram. In complete analogy with this, the unit of mass in the English system, one of them, the standard unit of mass, is, well, you know the force. It's kind of weird. Most people don't talk about weighing newtons, but you do, and they do know the unit of mass, it's kilograms. But in the English system, it's the reverse. You know the unit of weight. The standard is a pound, which is abbreviated LB. And we want to give a name to a pound per foot per second squared. And the name of this, apparently for a long time this didn't have a name, this is called a slug. Slugs are not very well liked in the literature. I've seen many students take a problem given to them in slugs, pounds, feet, seconds, and they convert everything into the metric system, into newtons and kilograms and meters, solve the problem there, and then convert back. People hate slugs so much. You really shouldn't be afraid of them. They're completely analogous to what you do in the metric system. It's just different. Anyway, the unit of mass is a slug. Some people talk about a pound mass. I will not. A pound mass is the amount of mass that would weigh 1 pound. I will not deal with a pound mass. So this means that, in complete analogy with the metric system, how much does a slug weigh? So if you take one slug and you have it at sea level on Earth, you would multiply times the acceleration of gravity, which is roughly 32 feet per second squared, right, to get that it weighs roughly 32 pounds squared to get. So just like 1 kilogram weighs 9.8 newtons, one slug weighs 32 pounds, which means a pound mass is 1/32 of a slug. So anyway, all right, I wanted to get that out of the way, but now let's do some problems. I want to look at a hemisphere of radius r, and I want to assume that it's filled with some highly compressible material so that the weight of the stuff at the top smushes the stuff at the bottom and makes it more dense. So things are going to be set up where our variable, instead of being x, will be z, and we'll see what the limits of integration are, but we're definitely going to do things in terms of z, not x in this first problem. So you have a hemisphere of radius r. I'm going to assume it's centered at the origin. This is, we'll call this the z-axis. So this is z. A hemisphere of radius r centered at the origin. An equation for it. Z equals the square root of r squared minus x squared minus y squared. And I'm going to assume that the density is a function of z. Let's see, there was a density function I wanted, is 1,000 times 2r minus z. Is 1,000 times 2r minus z kilograms per cubic meter. So what does this mean? It means when z is 0, your density is 2,000 r, whatever r is. So when z is 0, when you're down here at the bottom of the hemisphere, your density is 2,000 r. When you're up at the top of the hemisphere, where z is r, you would get half of that, because then you'll get 1,000 times just r. So whatever this hemisphere is filled with, we're assuming it's twice as dense down here as it is up here. And the question is, so this is the density. The question, what is the mass? Of this filled hemisphere? Well, you take density times cross-sectional area, multiply times dz, and you integrate as z goes from, will go from 0 to r. So yes, z will go from 0 to r. We have our density function. Our question now is, what's a of z? Well, we actually looked at this when we did volumes, but I don't expect you to remember exactly everything we've done. So if you're at some z coordinate, the question is, if you take a cross-section perpendicular to that z coordinate, you get a circle, or actually a disk, a filled-in circle. And the question is, what's this radius as a function of z? Because if we knew that radius, then the area of the cross-section would be pi times the radius squared. So how do you figure out that radius? Well, it's easy. Here's the origin. This distance out to here is r, and this is z, and then you use the Pythagorean theorem. So you get that z squared plus r squared equals capital R squared. So that first r was a little r. So we get that the mass, let me go ahead and write. So what's a of z? It's going to be pi times r squared, where what's r? R of z. What we just said is r of z squared, so r is r of z. And what we just said was that z squared plus this r squared should be, little r squared, should be capital R squared. which means that little r squared is capital R squared minus z squared. So that this cross-sectional area, little r squared, is capital R squared minus z squared. So this is pi times, it's right here. It's already squared for us. Pi times r squared minus z squared. So that's the cross-sectional area. And as I said, you should think of these things in pieces. So the little chunks of volume be the cross-sectional area times a little thickening. So you get pi times r squared minus z squared times dz. And that's dv. And then dm, a little blob of mass, is the density times a little chunk of volume. We know the density, we're handed the density function. It's 1,000 times 2r minus z times dv, but we put in that dv is this, so we get that times pi times r squared minus z squared dz. And then, yeah, we want to add, so that's a time symbol, it's supposed to be. And then we want to add up all of these as z goes from 0 to r. So we integrate. This won't be too bad. It's not particularly attractive, but it's not so bad. So what do we get? We get the mass is the integral from 0 to r of, I'm going to put the constants out front. We get I'm dropping all the units. We know what they are. Density was in kilograms per cubic meter. The volume is going to come out in cubic meters. Well, I didn't say that I was measuring all the distances in meters, but I was. So that our mass will come out in kilograms. I'll just suppress the units until the end. Hopefully I won't forget to put them in then. We get 1,000 pi times 2r minus z times r squared minus z squared dz. How do you integrate this? Well, it's easy. You pull out the 1,000 pi. It's a constant. Just the easiest thing to do is just go ahead and multiply this out. You get a polynomial. You use the power rule. And you get whatever you get. You get 1,000 pi times the integral from 0 to r of, all right, you get a 2r cubed, and then a minus 2rz squared, and a minus r squared z, and a plus z cubed dz. You get that, and then you use the power rule repeatedly. So remember that r is a constant, so this is just some constant integrated with respect to z. So there we just get 2r cubed z. But then here you get a minus 2r times the power rule done to z squared. You add 1 to the exponent, divide by the new exponent, minus r squared times power rule here. The power exponent is a 1. You add 1 to the exponent, divide by the new exponent. Same thing here, z to the 4th over 4, and you evaluate as z goes from 0 to r. And certainly when we plug in z as 0, every one of these terms becomes 0, so what we get is this quantity with z replaced by r. So what we get is 1,000 pi times, when you put in z as r, we'll get a 2r to the 4th minus 2/3 r to the 4th minus r to the 4th over 2 plus r to the 4th over 4. We could certainly get a common denominator of 12ths. I guess I won't bother, but you could. And this will come out in kilograms. All right, if you're wondering why all of these had to come out with r to the 4th in them, well, our units, to work out right, we better kind of have the same power of r here each time, or something's not not right, because if you had an extra power var or one or lesser power var, then one of these things wouldn't be multiplying correctly to make us end up with kilograms. All right. So that's how you can do a kind of a three-dimensional solid density and mass problem with just one variable calculus. You have a formula for the cross-sectional area, and you assume that in each cross-section, the density is constant in a given cross-section, but can change as you change the cross-sections. Because we found volumes another way, there is another way you could get an interesting one variable problem out of a solid object, and that's we could generate our solid as a solid of revolution and use cylindrical shells. Then we have to make it, we once again will have to assume that our density is constant in each shell, and so that means we're assuming something special. So I want to go back to a region we looked at in the volume section. So let's look at this example where we have y equals 2 minus x. Here's y is the square root of x. These intersect at when x is 1, and y is 1, and this is 2. And we want to look at this region and revolve that around around the y-axis and generate some, I don't know, it's kind of like a cool top, so, a top that you spin. You revolve that around the y-axis, and we'd like to get a mass problem out of this. We found the volume of this before. We used cylindrical shells. So what you do is you take, instead of taking cross sections that are perpendicular to your axis of revolution, you take a cross section that's parallel. So a cross section of the original region that's parallel to your axis. And when you revolve that around, you get a cylinder, but then you thicken the cylinder a little bit, which means you can think of that as starting with a little thickened rectangle in the first place and sweeping that around. Well, that means you'll have an infinitesimal little change in x, right, for the thickness of your cylinder. And then what did we do? You take, if you call that the radius, the distance from each cross section to the axis that you're revolving around, call that r, and you call the height, call this the height of this cylinder. Well, the formula for the area of a cylinder, 2 pi r h, the circumference of a circle times the height. But then you give it a little infinitesimal thickness, and this will give you a little chunk of volume. This is what we did when we looked at cylindrical shells. Since our axis of revolution is the y-axis, the distance from what you're revolving to the y-axis, so the radius, is just the x-coordinate. So in this particular case, r will just be x. The height is, well, it's the difference between the y-coordinate on this curve and the y-coordinate on that curve. So the upper y-coordinate is given by y equals 2 minus x, so h is 2 minus x, minus this y-coordinate, and that y-coordinate is the square root of x. So for our little chunks of volume by cylindrical shells, what we get is 2 pi x times 2 minus x minus the square root of x dx. Great. How do we turn this into a mass problem? What we need to assume now is, if we want to just do one variable integrals, which is what we want to do, we need to assume that our density just depends on x. So as x goes from 0 to 1. So but that means as x goes from 0 to 1, what you're getting are, you'll get the shell that corresponds to this x coordinate, you'll get the shell that corresponds to this x coordinate, and you'll get the shell that corresponds to this. As your x goes from 0 to 1, you don't just get these pieces. That's just telling you the x coordinate that you then revolve to and calculate the volume of the corresponding shell this way. So your x coordinate, don't think, oh, well, I should go from -1 to 1 and I need to get all this revolves. Oh, we've already encoded what you get by taking something at this x coordinate and revolving it. Now you just need to let x go from 0 to 1 to pick up what happens at each of the points in this region. But we need to assume that our density is just in the solid that we generate, that delta just depends on r, the distance to the axis of revolution. So that I'm going to assume, I just picked a function, 200 times 1 plus r kilograms per cubic meter. I just made this up. And so what this means is when you're right at the axis of revolution, so that r is 0, the density along points there, it's 200 kilograms per cubic meter. As you get out here where you're a distance of 1 away from the axis of revolution, and you would be at all the points that, you should picture this as some kind of circular look or top looking thing. This is swung around, it's revolved around, so there's this whole circle of points that you get from here when you swing this around. So on that outer circle edge, that would be where r is 1, and the density out there we're assuming is 200 kilograms per cubic meter. But we need that it depends that all the points in each cylindrical shell have the same density, otherwise we're not going to be able to do this, and that means that we need for the density to just be a function of the distance to the axis of revolution. In this case, as I said before, r, the distance to the axis of revolution, is just x. And so we get this, and then it's a one variable problem now. And I'm not going to finish this integral, but let me set it up. In a lot of these application problems, the interesting part is setting up the correct integral. Actually evaluating it is, it is what it is. So it's not uncommon or it's fairly common for instructors to make tests slightly shorter by just having people set up some integrals and not actually evaluate them. But you, of course, should pay attention to whatever instructions you're given. So the mass. The mass will be the integral as x goes from 0 to 1. 0 to 1. You'll add up all the infinitesimal blobs of mass. What's an infinitesimal blob of mass? An infinitesimal blob of mass, well, it's density times an infinitesimal blob of volume. Okay, so what's an infinitesimal chunk of volume? We're using cylindrical shells, so we got, I'll put in the density function too. So we got 200 times 1 plus x for the density. And then the volume using cylindrical shells, we got 2 pi x times 2 minus x minus the square root of x dx as x goes from 0 to 1. This again, I've set this up in kilograms and cubic meters. And again, I didn't say that all our distances were measured in meters, but I meant that they were. And this will come out in kilograms, the total mass. How hard is this integral? That's just the power rule over and over again. You'll pull out a 400 pi, multiply these three quantities together. You just have powers of x times constants. Just use the power rule. All right. Those are two examples of how you find mass given density of solid objects. But in one variable calculus, you're frequently given kind of simplified problems that are more clearly involve just a single variable like x. So I want to talk about length density and area density. These are kind of idealized densities. We can make sense of them in terms of real, actual, three-dimensional volume densities, but we don't usually talk about them that way. So suppose you've got a thin wire. So think thin wire. And what we really mean is we have an idealized one-dimensional object, that it only has one dimension, and that's its length. Then, so maybe it goes from x equals, suppose it's laid out along the x-axis, and it's between x equals a and x equals b. Okay, so you've got this thin wire. Then what people normally talk about in this case is length density. And I'll write a delta, but with a sub L for length. The length density. And this is mass per length. So what that means, and it's the infinitesimal, so if infinitesimal mass divided by infinitesimal length, so it's dm dx if you're measuring, if you've got things laid out along the x-axis. And it can change as x changes. So I'm going to write this as a function of x. And so reading this in terms of infinitesimals and writing it in terms of differentials, what you get is an infinitesimal blob of mass is the length density times little changes in length. What do you mean the mass per length? All right, this is how people talk about the mass of a wire, that it has some mass per foot or per meter. It's you could set this up as a three-dimensional problem, and so if you want to think of it as, well, yeah, what does that mean? Well, yes, it really, you can picture the wire as being fatter, blow it up, so look at it and go, oh, it's not, it's not a one-dimensional thing, it's a three-dimensional thing. If you want to do that, then you need to set things up. You would set things up the way we set them up before. You would have to assume that you have a cross-sectional area function, and that in each cross-section, the density is the same. For a fixed cross-section, the density at all points in the cross-section are the same, but the density can change as x changes. So that we would do what we did before and get O. So then dm would be delta of x times a little chunk of volume, and a little chunk of volume so this is the normal three-dimensional density, so mass per volume. And then you'd write that dv is ax dx. And what that means is we'd get little chunks of mass given by this expression instead of by this expression. Well, that means that if you want to think of it as three-dimensional, in terms of three-dimensional densities, then what you're doing is defining the length density to be the everyday ordinary density, so volume density, times the cross-sectional area, and you're assuming that the density doesn't change in each cross-section. So I suggest you not think of it that way. It's if you're trying to make sense of, oh, but length density doesn't really exist. Yes, it does. We can do that. But this is how everybody talks about it, and this is how I'll talk about it for the rest of the time. It's also true that you get an area. You can talk about an area density in the same way. You can make this rigorous in terms of volume densities, just as I did, but the way people talk about area densities, you've got some idealized two-dimensional object. So one of our examples will be a triangular metal plate. So think of a thin metal plate. There's a vocabulary word that you can use for really thin plates, a lamina. I probably won't say that often. I prefer to say a thin metal plate. But we're thinking of it as an idealized two-dimensional object, that it really, for most intents and purposes, it only has 2 dimensions. And then, of course, we'll talk about area density. And area density, which I'll write as delta sub A, is mass per area. But of course, we mean this infinitesimally, so we'll have a dm dA. And we'll need it as a function of a single variable. So in this kind of problem, we would have to assume that either we're doing things in terms of x, and the density is constant in each x cross-section, or that we're looking at this in terms of y, and the density is constant in each y cross-section. But one way or the other, we have to turn it into a one-variable problem. And then, of course, we'll read this as the infinitesimal contribution to the mass is the area density function times area. Okay, so let's just do one problem of each kind, and then we'll be done with this section. So, it could say most anything. So let's suppose we've got a wire. So, an example. Suppose we have a wire. Laid out along the x-axis. Between, I think I want x equals 0 and x equals 4. And I guess I'll switch to English system and use feet. Suppose the length density, so delta sub L of x, is, I want e to the minus x. Slugs per foot. Oh wait, as far as I know, there's no abbreviation for the unit slugs. You just keep writing slug. So the density when x is 0 is 1 slug per foot, but when x is 4 is e to the minus 4, so 1 over e to the 4th slugs per foot. So it's much less dense on the right than on the left. And we could ask lots of questions, but let's just let's just go ahead and figure out the mass between 0 and 2 and the mass between 2 and 4. Of course, the mass between 0 and 2 is going to be bigger. Why? Because the density is a lot higher down close to where x is 0 and gets much smaller down where x is 4. How much more dense, how much more mass does the left half have than the right half? Well, let's just see. So the mass of the left half. So I mean half in terms of distance, certainly not half in terms of mass. Mass of the left half. This will be the integral as x goes from 0 to 2 of your length density times little chunks of length. Right? I guess to be consistent with writing it in pieces like I was doing before, I would first write, to find the mass, you want to add up all the little blobs of mass. But now, since we've got an idealized one-dimensional object and are dealing with length densities, that little blob of mass is just the length density times little chunks of length. So these problems are kind of inherently easier than the ones where we had a solid object. You get the integral from 0 to 2, our density function, e to the minus x dx. either by making the substitution u is minus x, or just by, you can think in your head, what's something whose derivative is e to the minus x? Well, it's almost e to the minus x, but then you pick up an extra minus sign. One way or the other, you should find that an antiderivative of e to the minus x is minus e to the minus x. And of course, now that's easy to verify because you can just take the derivative of this, see that you get this, and you evaluate from 0 to 2. This gives us minus e to the minus 2 minus what you get at 0, which is minus 1. And so we get 1 minus e to the minus 2 is 1 over e squared. I think I'll write it that way. This is slugs. If you wanted to get the weight of the left half, you would now multiply this by 32 feet per second. So multiply by 32, and that would give you the weight, well, approximately, because 32 is only approximately the acceleration of gravity, but in pounds. Slugs, feet, seconds, pounds. So if you multiply this by 32, you'd get the weight of the left half instead of its mass, and that would make a lot of people more comfortable. But what's the mass of the right half? So, the mass of the right half, which should be a lot smaller. Now you do exactly the same thing, except now you integrate from 2 to 4. So we'll just integrate from 2 to 4, e to the minus x dx. So you get minus e to the minus x evaluated from 2 to 4. So we get minus e to the minus 4 minus what you get at 2, which is negative e to the minus 2. So minus minus, that's a plus. So we get a 1 over e squared minus 1 over e to the 4th. And this is in slugs. And yeah, this is significantly smaller than what we found before, which was 1 minus 1 over e squared. So the calculation's easy. Why is the calculation easy? Because I picked an easy length density function. I want to do one area density problem, and then we'll be finished with this section. So let me take a thin metal plate. So an idealized two-dimensional object. So let's take y equals 2 minus x and assume that we have this triangular plate right here. So think thin metal plate. And I'm going to assume that it has an area density function. It's a function of y. And so this means that I'm going to be assuming that the density in this plate is constant along horizontal lines. So for each horizontal line, each horizontal cross-section of the metal plate, the density is constant everywhere, the area density. And I'm going to assume that that area density as a function of y is, just to continue picking on e to the minus x or e to the minus y. I'm going to assume it's this, but now in, say, kilograms per square meter, and I'm assuming that this is measured in, all the lengths here are measured in meters. So this is at 2 meters. This is at 2 meters. Okay, then find the mass of the plate. Well, the mass then, you would integrate as y goes from 0 to 2. You don't have a choice here. If we were finding area, and hopefully you'd know the area of a triangle and you wouldn't integrate to find the area, but if we were using integrals to find the area, you could do integrals with respect to y, think of little infinitesimal rectangles, horizontal rectangles, or you could do integrals with respect to x and think of vertical rectangles. We don't have that option now because our density function is a function of y, and if we tried to do things in terms of x, then we wouldn't know the density is constant in each of our cross-sectional things, and we wouldn't be able to get anywhere. So you integrate as y goes you add up all the little blobs of mass as y goes from 0 to 2. But a little blob of mass is the area density times a little blob of area and put in the area density function that we were given. So you get the integral from 0 to 2 of e to the minus y, and then dA. dA, if we're looking at things in terms of y, at a given y coordinate, a little chunk of area, it's this length times a little thickness, so a little dy to give yourself this little chunk of area of this rectangle. So what is this? Well, this length is the x-coordinate on that curve. But in terms of y, that x-coordinate, you put the x over here, the y over there. In terms of y, that x-coordinate is 2 minus y. Okay, so we get, there's the area density function, and then a little chunk of area, you get that it's this length, which is 2 minus y, times the infinitesimal little thickness, dy. And this is all going to come out in kilograms. Now, I'm not going to finish this integral, but you should, and it's in the book. It's how do you do this integral? How do you find an antiderivative of this? Well, if you look at it for a few minutes, hopefully it would occur to you what you do. To calculate that integral, you need to split it into pieces. So we would have to, you want the integral from 0 to 2 of e to the minus y times 2 minus y dy. You multiply the e to the minus y times both parts. You get 2e to the minus y e to the minus y dy. You can split this integral up. You know how to anti-differentiate that part. Right? So you could split this integral into these two pieces. This first part is simple. In fact, we've just done it a couple of times. But it's the second part that might look bad. So this is easy. An antiderivative of e to the minus y minus e to the minus y. You just pull the 2 out. You evaluate from 0 to 2. So that part's easy. How do you do this integral? Hopefully, if you look at this for a few minutes, you'll remember our techniques of integration. You do this by parts. By parts. So you would let u be y, and that would leave e to the minus y dy for dv. So dv then would be e to the minus y dy. And then you use integration by parts, which I remind you is, in terms of u and v, is the integral of u dv is u times v minus the integral of v du. And this choice will enable you to do this. You now find that du is dy. You find that v is minus e to the minus y. And you apply integration by parts, and you can do this integral. But I'm going to leave that for you to do. In the next section of the book, we're going to look at centers of mass. Originally, I had this material in the same section as the mass and density, and I realized it was getting very long. But the center of mass is a cool concept, but you have to have mass and density under your belt first before you can talk about the center of mass of an object, which is kind of a point that you think of as kind of, for a lot of purposes, you can think of your mass as being concentrated at that single point in space. It's kind of cool. Anyway, we'll do that in the next section.